So the solution that the National Science Foundation is working toward is to move this the 30-meter telescope to the Azores, to Tenerife, maybe? So speaking of, so here are the locations of the big telescopes. So this is on the Canary Islands. This is a Spanish or European telescope, and they have a reasonably good site there on the big island of maybe Tenerife. The Australians kind of struggling. They don't have any high peaks. They're seeing, the whole continent is not that good for seeing. And then they had a big fire here at Siding Spring, not this year, but 6 or 7 years ago. The whole place was destroyed. They had to rebuild it. Mauna Kea. Texas. The McDonald Observatory in West Texas is the most advanced in the continental United States. There's the VLT in Chile, that's the product of the European Southern Observatory. Canadians, they got issues. They're on the kind of, in British Columbia, on Vancouver Island. It's not really very good. There's a OK telescope in South Africa. It's the biggest one, in the continent of Africa. And then there's one in India. So let's talk a little bit more about this optical interferometry thing. This is a picture of the two Kecs, each with 10-meter segmented mirrors. I was just saying during the break that the University of California, Santa Cruz, which is prominent in this, in managing Keck's development, wanted to put additional mirrors here to build a really top quality interferometer, but the protest has kind of derailed a lot of stuff. And I actually don't know what the status is of interferometric work on the summit. Here's the Navy owns this thing. It's called NPOI, the Navy Prototype Optical Interferometer. It's out in West Texas. See, it's a Y-shaped thing. That's an experimental facility. But here's the idea. This is VLT seen from outer space. These are the 4-unit telescopes I talked about. And then they can position these other guys as need be, and then draw a circle around that whole thing. In fact, there's the circle. So you can simulate a telescope 130 meters in diameter by getting all these guys to work in coordination. And if you see the technology involved, it looks like a lot like a model railroad. So like if you go to Golden to the model railroad, the railroad facility, they have a train set the size of this room. When the light comes from each of these telescopes, it comes into what's called a beam combiner room. And there are trolleys with mirrors on them. And as the telescopes move, as each telescope rotates to follow the target, the trolleys move to keep everything the way it's got to be, so that the beams from all these telescopes can be properly combined. So if you stand there, you see the little trolleys are moving. One's going this way, one's going that way, and then they back up, and it looks like a model railroad. And it's based on this idea. This is the desert in Australia. Here's the VLA. This is the Very Large Array, which is a radio telescope facility in the desert in New Mexico. It's out west of Socorro. And then this is the next generation. This is the European stuff called ALMA, which is the first letter comments on the desert in Chile. This is the Atacama Desert, where that array is. And then there's the old conventional style, which is a big dish. That dish is pointed upward right now. It's in West Virginia, Green Bank, West Virginia. That's a radio telescope. It looks like I wrote over a piece of art, and I apologize. There's art back here. But when I was a student, the Green Bank telescope, which is huge, collapsed because it has big motors to move it and tilt it, and one of the bearings in the facility froze, because they're all exposed to the weather, and the motors kept going, and it just thunk, the whole thing collapsed. It took 20 years for Robert Byrd, the senator, to get the funding to rebuild it. So back in '98, I was at the Keck, so here's me, there's Subaru, and there are the two Kecks. You can see these guys from the beach. The domes are so big, in clear weather, you can be standing on the beach on the west side and look up and you see two little white dots, and they're 30 miles away. There's my wife with the dome in the background. This is some of the complexity that's involved in keeping the mirror aligned even when things are moving around. Watch out for cows. The invisible cows, yeah. And this is similar to that video I was telling you about where I was getting vertigo. This is, everything you see is moving. It's just, you gotta close your eyes or you'll fall down. So, here's a little more detail. This is one segment of this. It's made of a ceramic product that has a lot of iron in it. It actually can be machined. It's called Zero Dur, but it has very good thermal properties, stability when temperature changes. And you can see through it when the metal film has been removed. So here's, it gives you a sense of scale. And then before it's put up here, they flash aluminum on that, and they have a production line. So every day, now maybe not every day, but once a week, they might take two petals out and put them in the production facility, strip off the aluminum coating that has oxidized, put it through an acid bath to get that done, then flash a new coating on and put it back in place before they have the next opportunity to do astronomy. Yes?
Why don't they use something like gold that doesn't oxidize?
It's good. Good question. The problem is, if you look at gold, you see a color. The gold itself does not reflect all colors equally, right? So, gold. Now, there are certain wavelength regimes in astronomy where a gold-coated mirror can work in the infrared because it has uniform reflectivity. But in the visible, it has a color of its own. So now let's talk about what's coming next. Here's a transmission curve, 100% opacity. So if you're down here in the very shortest wavelengths, like gamma rays and X-rays and part of the ultraviolet spectrum, the atmosphere completely blocks you. You cannot do astronomy from the ground. Here's visible wavelengths are here, and we have what is called a window. We can see, except in the deepest blue, just outside of what humans can sense. And there are these various windows. Most of these are the result of water vapor in the atmosphere. We have a nice window for radio waves.
From the South Pole.
And the South, well, anywhere radio propagates from the sky. We all know this because you have a satellite dish, you're getting a radio signal from a satellite. To really do astronomy, you want to be where it's as dry as possible because water vapor is the limiting factor. So now, here, important thing is the James Webb Space Telescope, which is the next big thing coming, we hope, in 2022. Its sensitivity in wavelength is shown by this arrow. It can see it in the visible some, but it's mostly designed to get out into the infrared for a couple of reasons I'll describe. Hubble has this, so we end up with this kind of comparison. In the news media, you'll frequently hear that James Webb Space Telescope is going to replace Hubble. That is not true. The James Webb Space Telescope cannot see into the deep ultraviolet. Hubble can. Hubble cannot see deep into the infrared. James Webb can. So one is not replacing the other. More on James Webb in a second. So, oh yeah, two reasons why we want to look in the infrared. One, we've discussed in this a couple weeks ago, we talked about seeing through dust. So the analogy I like to use is if you're out driving in a rainstorm, there's some impact on your vision, but if you turn all that water into tiny droplets we call fog, your visibility is completely ruined. You probably can't, in a deep fog, you can't see more than a foot or two. It has to do with the size of the particles floating in front of you compared to the wavelength of the light you're trying to use to visualize things. And because there are dust particles, dust and molecules in all these galaxies that we've been talking about, going to the infrared gets you to a wavelength where that dust is not so important. And here's a comparison. In the visible, you can see this, and in the infrared, you see this. You can see right through. So James Webb is designed to do that. The other reason that we want Webb to be a success is the ancient galaxies that we are limited in our ability to study are moving away from us because they're ancient. They're moving away from us at a high rate of speed, which means their signals are shifted into the infrared. If you are local to those galaxies and they're producing a lot of ultraviolet and X-ray light, because of this expansion of the universe, that light appears to us to be reddened dramatically. So James Webb is designed to be able to see galaxies that are far, far away, meaning they're very old galaxies. So once again, we get to see deeper, and you get to actually do science on galaxies we cannot visualize now. So here's more on James Webb. It's stupendously complicated. Here's the sun, here's Earth, there's the moon. This thing is 1.5 million kilometers away from Earth, where it can get really cold. It's important in the infrared to do good science. The detectors you use and the mirrors you use have to be cold. Otherwise, all you see is the glow of the mirrors. If we had an infrared camera here and I pointed it around, you would see the humans are prominent because they're glowing. They're at 300, most of us are at 300 Kelvin. Maybe a little higher if you're sick, a little lower if you're old. But around 300 kelvins is the average temperature of a human body, and you're glowing. If you point that same infrared telescope at an ice cube, you don't see much because it's cold and it has less self-emission. So for this to work, the big mirror, which you see faintly is made of hexagons, the mirror has to be cold, and the detector assembly, all the sensors, which are back here, have to be cold. So to make that happen, we have this incredibly complicated layer of multiple layers of mylar, thin, kind of like the sandwich bags, covered with metal of the right type, and there's 8 layers designed just in the right way to keep sunlight from warming up the telescope. But we do need sunlight to warm up the spacecraft, because the spacecraft has electronics that like being at room temperature. Immensely complicated, very expensive. Here's how it compares in size to Hubble. Here's the primary mirror of Webb, the person there, 6.5 meters. And here's our 2.4 meter Hubble telescope. But the same idea. The primary mirror has a hole in it, so the starlight hits that, hits the secondary mirror, goes through the hole, and finds its way to the instrumentation. So let's look. This video I do want you to see. So Guyana, French Guiana, very close to the equator, which helps the energetics of lifting a large mass. And the rocket comes from Europe. That's their contribution to, and they're building an instrument as well. So the rocket gets launched on the north coast of South America. This is a simulation, of course. A big rocket. This is an Ariane 5. It's the biggest rocket going right now. And up she goes. Let's see. Oh, this one too. So Arianespace, a French consortium, lifts the rocket, and then things really get complicated. Solid rockets go away, nose cone comes off, and here is the James Webb Space Telescope folded up like a rose. And this is the business that we care about. So this thing is going to unfold while it's on its way to its where it's going to do science, which, as I say, is 1.5 million kilometers from Earth, at a special place where it's sort of a little bit of a depression in the gravitational field from Earth, the Moon, and the Sun, and it can just live there with just a little bit of tinkering. So first, solar panels come out so you can make power, because everything else is, there's hundreds and hundreds of electric motors on this thing. In the narration, they're talking about why we're doing this. So notice the time here. So we're a half hour into the flight. We're on our way to the operational point. We need power, so we're flipping out the solar panels. Now we're advancing hours every few seconds. So we're up to 7 hours. Let's get that out of the way. Still maneuvering to get to the right place. So this will be a tense time. Antenna comes out so you can talk to the vehicle. This is one row of the beryllium mirror system that we were talking about, using a different kind of material, not glass, to support this, because beryllium extremely stiff and low mass. It's just very challenging to work with. Now the telescope itself moves away from the spacecraft, which is going to reveal itself here in a second. Now, these are those foil, this is the deployment mechanism for those mylar sheets I was talking about. Each one is the size of a tennis court. And you can poke your finger through them. I mean, nothing can go wrong when you're doing this. There's the primary mirror before the two panels have winged out. That comes later. And then you have this mechanism to drag out the mylar sheets. As soon as you do this, the telescope temperature is going to start dropping, because this blocks, the sun cannot illuminate the telescope, which is this business here. So now we have the mylar sheets are out. Now we're in the 6th day. This is the spacecraft. This has to stay warm. And it has all the navigation technology and communications. And there's the secondary mirror popped out. This is a radiator to help cool down the telescope. So all the surfaces that aren't pointing at Earth are pointing at deep space. So heat can be radiated away. Now we have the primary mirror deployed. 17 days into the flight. You're not yet at the operational location, so there's a little... Now, everything here is sensitive to contamination. So the thrusters are not chemical. They're ion thrusters that won't contaminate the mirror. So here's the trajectory of the spacecraft. Can you see it's kind of looping around a point. Let's go back. The point is orbiting Earth. There's the point I'm talking about. It's called a Lagrange point. And the spacecraft is orbiting that point with just occasionally a little putt-putt of thrust to stay there. And that's what it will do for the entirety of its mission.
How long is its mission?
It doesn't have any consumables for the science. It does have consumables for staying at the Lagrange point. 6 years? I'll say this. NASA has a spectacularly good record of exceeding the design life of its missions. I mean, Hubble, which has been serviced multiple times by astronauts, is at 22, is at 20 years, and expected to last till at least 22 years.
How far is this from Earth?
I think I have a picture. It's 1.5 million kilometers.
Simple.
I think I have a picture coming up, but here it is in the test facility. More details here at this YouTube